Okay, in this video, we are going to discuss on tutorial 17, deformation of solid. So, question 1. A load of 5.0 kilogram hangs from a vertical copper wire of length 2.50 meter and cross-sectional area 1.00 millimeter squared. So, the extension of the wire is 2.80 millimeter. Calculate the stress, the strain of the wire. Okay, the stress, we look at the what is given in the question. So the question give mass 5.0 kg, length 2.50 meter and cross-sectional area 1 millimeter squared. And another one is extension 2.80 millimeter. Okay, to calculate the stress, the formula is F over A. So the F, the force we can use mg. So the mass is 5 kilogram times the g value 9.81 and the area 1 millimeter squared convert to meter squared. So 1.00 times 10 to the power of negative 6. So you get the answer 4.91 times 10 to the power of 7 Newton per meter squared. Okay, next to calculate strain, we use formula strain, extension over length. Extension is given 2.80 millimeter, convert to meter, divided by length of the wire, 2.50 meter. So you get strain to 1.12 times 10 to the power of negative 3. Okay, next question. A wire of natural length 3.60 meter and diameter 0.50 millimeter is stretched by forces of 250 Newton. The strain in the wire is 4.0 times 10 to the power of negative 4. So what is the stress? And then find the extension of the wire. Okay, the stress, to find the stress, so look at what is given in the question. So you are given length 3.60 meter, diameter 0.50 millimeter, and the force 250 Newton. Okay, so the stress, and another one is strain 4 times 10 to the power of negative 4. Okay, the formula for strain, for stress is force over area. So we use force given 250 Newton divided by area. So we assume that the cross-sectional area of the wire is circle. So we use pi r squared. So r is diameter divided by 2. So 0.50 convert to meter times 10 to the power of negative 3 divided by 2. So then squared, so that's why here 4 divided by 2, so 2 squared is 4. Okay, then the answer is 1.27 times 10 to the power of 9 Newton per meter squared. So the common mistake students make every year is by using the F here, they total this up, 250 Newton plus 250 Newton. So that is wrong. Okay, now B, find the extension of the wire. So the formula for extension, we can use strain formula because strain is given. So strain is extension over length. So you substitute the strain 4 times 10 to the power of negative 4. E over 3.60, the length of the wire. Okay. Then the answer, extension is 1.44 times 10 to the power of negative 3 meter. Okay, question 3. A copper wire is stretched beyond its elastic limit. So what is meant by elastic limit? And then sketch the stress strain graph for the copper wire. And question C, the stress is then slowly reduced to 0. Show on the same graph how the stress varies with the strain during the unloading. Label your graph clearly. Okay, first question, what is meant by elastic limit? So elastic limit is the maximum stress a material can withstand before the permanent deformation. And it is the material's highest limit before the material's plastic deformation can occur. So once the stress or force is removed from the material comes back to its original shape. Okay, now question B. Sketch the stress strain graph for the copper wire. Okay, so the graph stress against strain, it looks like this. Okay, the label P is the proportional limit, and the E is elastic limit, and Y is the yield point. Okay, and U is the ultimate stress point or breaking stress, and lastly F is the fracture point or breaking point. Okay, next question C. The stress is then slowly reduced to zero. Show on the same graph how the stress varies with the strain during the unloading, and then label your graph clearly. So this is uh, the the line that load, label the graph clearly. So this is the loading and this is the unloading. So it won't, after the elastic limit, so it won't come back to its original strength, because the copper wire is stretched beyond its elastic limit, so it follow the new linear graph. Okay, next we go to question 4. The extension force graph of two wires X and Y of the same material but of different lengths and diameters are as follows. So the table below shows the length and the diameter of the wire. So calculate the force constant of the wire X, the Young modulus of the material of the wire, and the diameter of the wire Y. Okay, to find the force constant of the wire, so we use formula force equals to KE from the Hooke's law. Okay, so the force we read from the graph here, the force is 50 Newton. Okay, then the extension is 4 millimeter, so convert to meter, and we can get K equals to 1.25 times 10 to the power of 4 Newton per meter. Next question is Young modulus. Young modulus of the material of the wire. So the formula for Young modulus is stress over strain. So stress is force over area and strain is extension over length. So we rearrange the equation become FL over EA. So F over E we can get from the question A, which is equals to K. So K L over A. So the K value is 1.25 times 10 to the power of 4, and the length is 3.5. We read from the from the table 3.5 for wire X, because we use K for wire X, so we need to use length of wire X, and diameter is for area is pi r squared, so the diameter here divided by 2, and then is 2 squared is 4 lah, so this one supposed to be both bracket, so 2 is 2 squared also 4, so there's a mistake here. Okay, then the answer is 1.78 times 10 to the power of 11 Newton per meter squared. Okay, next we calculate the diameter of wire Y. So diameter of wire Y, we use the same formula of Young modulus, FL over EA, but this time the K, we cannot use the K of X. So the K we use, okay, for the K, we use the table here, okay, the length and the diameter, and the K is the new graph here, the K here. So we substitute the Young modulus, the same as B, question B, because it is made of the same material, same type of wire. So therefore, we can use Young modulus in B, 1.78 times 10 to the power of 11. Okay, then for the force and extension, we'll give you the new K, so we need to read from the graph for wire Y. So 50 Newton, force divided by extension 2 millimeter, convert to meter. Then the length is 2.4, okay, from the table, the length of wire Y. And the area, we use pi r squared, so r is d squared over 4. And we substitute into here and we solve, we get diameter Y of wire Y is 0.66 millimeter. So you can convert to millimeter. Okay, next question 5. The extension force graph of a wire is as shown below. Okay, so calculate the strain energy of the wire when the extension is 3 millimeter. So if from for the graph extension against F, so the strain energy is given by the area under the force against extension graph. But the graph here is opposite extension against F. So therefore, the area under the graph for 3 millimeter, okay, so we read here 3 millimeter will be at the top here. Okay, so area under the graph will be this side because this is extension against F graph. Okay, next it is the shape of a triangle. So half times force times E. So the base will be 40 times the height of the triangle will be 3 times 10 to the power of negative 3 in meter. So you get the answer 0.060 joule. Okay, and the strain energy of the wire when the extension is 6 millimeter. So for the graph, is until this area. So strain energy is area under the graph of extension force graph will be, we divide into 3 section. So section A, so B, and then the C section. Okay, so the area of A is we just used A question from the answer from A 0.060 joule calculated already. So area B is area of a trapezium. So half times the parallel line will be 40 and 50. Okay, 40 and 50. Then the height of the trapezium will be 1 millimeter convert to meter. And for area C, half times 50 plus 60, the parallel ray, the parallel line here. Okay, then the height of the trapezium will be 6 minus 4 will be 2 millimeter convert to meter. So you get 0.215 joule. Okay, so we use area of a trapezium for B and C. Okay, next, last question. An elastic cord of natural length 32.0 meter is tied to a bungee jumper of mass 50 kilogram. The jumper falls from rest from a height of 40.0 meter above a river. So in the first descent, the jumper just touches the water in the river. Assuming that the elastic cord obeys Hooke's law, calculate the loss of potential energy of the jumper, and then the force constant of the elastic cord. And the last question is the length of the elastic cord when the jumper finally hangs in equilibrium from the elastic cord. Okay, so the first question, the loss of potential energy of the jumper, so is change in potential energy, final minus initial. So mgh, so the loss will be mgh minus 0. So at initial minus at the when it touch the ground, the river, the river, so 0. Okay, so mgh, m is 50 kilogram, okay, the mass, and 9.81 times the height, 40 meter. So you get loss in potential energy equals to 1.96 times 10 to the power 4 joule. Okay, next question, the force constant of the elastic cord. So we use strain energy, which is equals to the loss of potential energy. Okay, strain energy is equals to the loss of potential energy. So strain energy formula is half KE squared, and then loss of potential energy we use from A. Answer 1.96 times 10 to the power of 4. Okay, so we substitute the extension. So 30, the natural length is 30 meter, and it touch the water at when the length becomes 40 meter. So the extension will be 40 minus 32. Okay, so don't forget the square, and you can calculate the K. K is 630 Newton per meter. Okay, then the last question. The length of the elastic cord when the jumper finally hangs in equilibrium from the elastic cord. Okay, by referring to the diagram or animation here, we have force act on the string, okay, on the elastic cord, and another force is weight of the jumper. So at equilibrium, these two forces are equals. So F equals to mg. So F is KE, so we use Hooke's law, KE equals to mg. So the K is calculated already in B, 613. So you substitute into the equation here, and M 50 kilogram and the G value is 9.81. So the extension of the elastic cord when it is in equilibrium is 0.80 meter. But be careful, the questions want length of the elastic cord. So the length of elastic cord, so the natural length 32.0 meter here plus the extension 0.80, so you get 32.8 meter. So this is the length of the elastic cord when the jumper hangs in equilibrium. Okay, so that's all for tutorial 17, and bye bye.